My name is Natalia Zelenskaya. I'm a software engineer at GrubHub, and today I would like to talk about highly available applications, cluster supervision, and data recovery. But before going into details and explaining how we do that, I would like first to introduce ourselves, tell who we are, what we do, and why we do that. So you will have an understanding of our business cases and why data recovery is so crucial for our business. GrubHub is an online food ordering and delivery company. Our primary market is United States, which in my opinion is a very unique market thanks to its rich variety. United States is known to be a country with diverse ethnicities and customs coming from different countries like China, Mexico, France. The list can go forever. Every time we talk about cultures, we talk a lot about food. And there are lots of nuances and differences. For instance, most of the Americans tend to have their lunch around noon and dinner around 6 and 7. While for Spanish, this is very early. On top of that, think about personal preferences or special requirements like allergies or diets. Think about people with physical limitations or who are just simply so busy that they don't have enough time to go to their favorite restaurant. So our mission is to make food available for everyone at any moment. We dream to help new chefs to establish their business and be discovered through our services. We dream to satisfy any diner's requirements, no matter how complex they are, and be flexible for them. We believe that people have different needs at different moments, and that's why we work hard to make it happen and to make our services available 24/7 for them, which sometimes might be really challenging. In our opinion, one of the ways to reach the high availability criteria when your service is available 24/7 without downtime is by using clustering. As you might know, clusters connect two or more services, so they appear as a single computing instance to a consumer of the service. Services connected into the clusters allows workload sharing, enables single point of operation, and provides a path for scalability to meet increased demand. Having these principles in mind, we decided to build a prototype framework on top of Akka and Akka clustering, which will allow us to host our application on a cluster, and it will have a built-in mechanism to supervise any in-memory states or important processes that we don't want to interrupt, and be able to react on any node failure and recover these states or interrupted processes. So let's take a look at the cluster and what makes so special about it if we start using Akka clustering with it. Here you can see a cluster of 4 nodes. These are 4 individual computing instances where we can host our application, and it will appear as a single service to our consumers. If we start using Akka clustering with it, it will give us a very interesting feature, cluster self-awareness. What this means is that all nodes in this cluster are aware of each other's existence. They use a well-known port for discovery to connect to each other, and they talk to each other about different events happening in the cluster using gossip protocol, on top of which Akka clustering is built. There is also a single node in the cluster that does a leader role. So this node is responsible for cluster convergence and membership state transitions. For example, if new node is going to join this cluster, it will use the well-defined ports to connect to all members, and by gossip protocol, they all be aware that there is a new node joining it. And it's leader responsibility to detect this node and make it as a member of the cluster. So it can say that member is up, there is a new node in the cluster. So also with the gossip protocol, you can get different type of events, including the node failure event. So for instance, if node 3 goes down, the whole cluster will detect that, and they will try to connect to it, but they will get a connection refused. So for some time period, they will try to connect to this failed node, and eventually the leader will say, this node is no longer available, we can remove it from a cluster and say that member went down. So how this information might be interesting, how we can get the most usage from it. In order to answer that, I would like to start with a real-life example, and you will see how we can recover our state using the recovery protocol based on Akka clustering. So imagine we would like to place a very tasty pizza order through GrubHub, and we would like it to be delivered here by 4 p.m. after the presentation. So the first step in order fulfillment process is sending this order to a restaurant to get the confirmation that they actually can prepare this pizza by 4 p.m. And ideally, they will send us back some estimations on delivery or pickup time. So what might seem a trivial data flow in reality is a complex system with different triggers, notifications, and means of communication. In order to be able to handle this complexity but still keep our code scalable, resilient, reactive, we can imagine that we can reproduce the order by stateful Akka actor. So this stateful Akka actor is going to manage the order's internal state and its life cycle. So here you can see different Akka actors that represent different orders. They have their internal state representing order in different period of its life cycle, and they also might have some scheduled jobs associated with them. These scheduled jobs contain events somewhere in the future that will trigger order state transition. For example, we can see our pizza order, and it has already a scheduled event at 3:15 associated with that. This might mean that at 3:15, this actor, stateful actor, will get an event saying that it's time to send this order to a restaurant. So we'll make a remote call at 3:15, sending a request to a restaurant to get a confirmation that they can fulfill it. For example, a restaurant receives an order, everything looks fine for them. They have ingredients, kitchen is available, so they confirm it. They send us back as well some estimations when we can come and pick up our pizza. Using this data, we can schedule another event associated with this order, saying at 3:50, we'll send a notification to a driver to go to a restaurant, pick up pizza, and bring it here by 4 p.m. So once we get our pizza, we can consider the order fulfilled, and we can shut down our stateful Akka actor. Throughout the day, we can get thousands of these orders, and if all of them are represented by stateful Akka actors, we want to use our computing resources efficiently. So we're going to redistribute them among the cluster of nodes. So let's take a look at the bigger picture. If we go back to our cluster, we can imagine that, for example, node number 4 already is hosting our stateful Akka actor representing pizza order and has some event scheduled in the future. So it's in memory state that we don't want to lose, and it's located on node number 4. Another example, node number 3 might have an order for crepes with Nutella. Someone has placed it, and it's already in a process of making a remote call to a restaurant to send a request for confirmation. So while in theory everything should work fine, we have in memory state, so the service should be super fast and efficient, in reality lots of problems can happen. So what if both of these nodes suddenly go down? We're going to lose our in-memory state that was located on node number 4, and we're going to interrupt our communication with the restaurant, which was happening on node number 3. So someone, imagine a friendly guy who will not get his crepes tonight. Not cool. So these crepes and this pizza are of high priority for our business. It is crucial for us to react immediately on any node failures and restore the lost in-memory states or recover interrupted processes. So imagine if we can implement an event-driven supervision framework, which will allow us to restore the lost data and reinitiate the processes that have been interrupted but are critical for our business. As I said, if you use Akka clustering, it has a gossip protocol with it. You can detect different events happening in your cluster, including the node fail event. So basically, in order to start your recovery process and be aware that something went wrong, you just need to listen to these events and do proper action on it. In order to initiate the recovery process and orchestrate it, you only need a single node in the cluster, which can be a leader node. There is only one thing missing at this point. How do we know which data has been lost or which processes have been interrupted? In order to answer this question, we can introduce the concept of recovery points. And I will explain what is it using an example. Imagine we receive a request to put a new order from the upstream service. So node number 2 received it, and as we decided, we're going to create a stateful Akka actor representing our order. But once the actor is created, we're not going to reply immediately to the upstream service acknowledging that we have handled the request. What we're going to do, we will ensure the durability of our supervised actor. We're going to persist the record in the storage with the following schema. We're going to say where our supervised task or supervised actor is located on. So we'll say, in this example, it's on node number 2. We're going to also record what's the time for execution of this supervised task, which can be any timestamp from now in the nearest future. It will have a unique identifier, some metadata, which can be a serialized JSON representing our order we're going to use later, and it will have a status. If the task is just become under supervision and it's not accomplished, it's always in flight. Only once it's successfully done, so for example, the scheduled event got transferred to the actor, or the remote call to a restaurant is successfully accomplished, we can consider it's done, and we'll update the status to done. In this example, we're just acknowledging the recipiency of a new order. We persist it with the status in flight. And only when the record is successfully persisted in the storage, we're going to reply back to the upstream service saying that we have handled the request and it's under supervision. Otherwise, if there was an exception, the upstream service is going to retry again. So let's see how recovery points are going to help us for recovery of a node. So if we go back to our cluster, we can see that, for example, storage contains already some recovery points in its tables. In this example, we can see that there are 2 records located on node number 3 that are still in progress and still under supervision. One record that has already been accomplished, and one which is located on node number 1, and it's still in progress. So now when node 3 fails, as we said with Akka clustering, we'll be aware of this event after some time. And a leader of the cluster, which might be a node number 1, can initiate the recovery process because it's aware that node 3 went down. So what it's going to do, it will use the recovery points to detect which data should be restored. So it will detect all in-flight records that used to be located on node number 3, which is our primary key. So it will pick up the first record and the third one. Once it has detected the recovery points we're going to use for restoring file processes or states, we're going to be smart about that, and we're going to redistribute the recovery among active nodes of the cluster. For example, one record for recovery might go to node number 4, and another might go to node number 2. The responsibility of these 2 nodes will, using the metadata that we have persisted, to restore the stateful actor representing any order or initiate any remote call that we want to accomplish. And also, they're going to update the recovery points to point to new location. So the first record will be pointed, will say that it's located on node number 4, and the third on node number 2. So maybe to better understand the concept of recovery points, we can do the following real-life analogy. Imagine you and your friend are coming to this presentation, and it's so interesting and exciting that your friend falls asleep. You notice that, and after the presentation, you start asking him questions if he remembers anything. You can say, do you remember slide number 1? He says, yes, perfectly. Do you remember slide number 2? Not sure. I remember something, but then I fell asleep. And you can say, you know, that might be interesting, and I have my records. I can start explaining the presentation starting where you have fallen asleep from slide number 2. So no information for your friend will be lost. We don't know exactly at which moment of slide number 2 he fell asleep, but we can replay it from the beginning till the end of presentation, and we guarantee at least once delivery of information to your friend. So this is the basics of our recovery protocol, and now I would like to jump in and do a small demo so you can see this happening in action. So this is a recording. I have a cluster on my local machine of 4 nodes, similar to the one we've seen on the presentation. They already have some in-memory states, which we're going to see on a dashboard represented by different metrics. And we're going to suddenly shut down our node number 3, and we'll see how the whole cluster is going to react on that, and we'll see the progress of recovery process depicted in the metrics. So these are 4 terminals from top left, representing node number 1, 2, 3, and 4. They already have some stateful Akka actors simulating our orders. And we're going to take a look at the dashboard, and we will see how many instances they have. So I'm zooming out, and we'll see that node number 1 has 1 stateful actor. Node number 2 has 2. 3 has 3, and 4 has 4, for simplicity. We're going to shut down node number 3, which has 3 stateful actors, and we're going to see how it's going to be picked up by all other hosts and redistribute among them. So I'm going to shut down the node number 3. And we will see that there is some activity going on. So all 3 nodes, which is 1, 2, and 4, are trying to connect to the failed node number 3. But they get connection refused. So we'll see this in the logs. In this example, the leader node is node number 1, which is going to initiate the recovery of failed node. So for a while, it was trying to connect to the failed node, but it got connection refused, which made think our leader that there is something funky going on, and after some configurable time, it can decide to remove the failed node from the cluster and initiate the recovery. So we can see that it logged that the member has been removed. So it's registering the resurrection of the down host and starting the resurrection. As we remember, our node number 3 had 3 in-flight records. And we can see that based on recovery points, it has detected there were 3 records that should be processed by the whole cluster. So now what it's going to do, it will redistribute these 3 records among active nodes of the cluster to keep the data balanced, and it will request resurrection from different nodes. So you will see 3 logs saying that it requested resurrection from different hosts for 1 record, which used to belong to the failed node number 3. We're going to see that all other nodes received this message, and they acknowledged the acceptance for resurrection. This is node number 2, and it's saying that it's resurrecting 1 in-flight record for the down host, that which just went down. When it successfully recovers the state and updates the recovery point, it says that everything was successfully processed. Same for the node number 4. So it received a request for a single in-flight record from failed node number 3. And it successfully resurrected it, which means, again, we updated the recovery points and recreated the state in memory. So the leader is well participating in recovery, so we can see exactly the same logs for the leader node. And after all resurrection has been successfully accomplished, we can see confirmations from the 3 nodes that participated in recovery. And at this point, because we know there are no more records to be recovered, we can consider the recovery of failed node number 3 successful. And we can see a log message saying successfully resurrected the down host. So we can also see what on a dashboard, because logs sometimes hard to read, especially because it's asynchronous message passing. we're going to see that the matrix has changed, that the state of our nodes has jumped one record above. So the host number 1 had 1 record, now it became 2 because it got 1 from the failed node number 3. And same happened to other nodes. Node number 2 jumped from 2 records to 3, and node number 4 jumped from 4 to 5. We also have metrics that show us different, this is a matrix that shows us the state, the current state of the nodes. We also have metrics that show the events. So it says that there was 1 resurrection of the host, which was orchestrated by node 1, which is a current leader of the cluster. And we also have an event metric that shows how many records have been recovered by each individual node. There are 3 graphs here, but because they overlap, it's hard to say. But on we can see down there that there are different metrics reported from 3 nodes participated in the recovery: node number 4, 2, and 1. Each of them got 1 record for resurrection. So this is a trivial case of our recovery protocol, but there are many edge cases that might occur during cluster lifecycle, and I will go through that, explain how we can handle them. So the first case, what will happen if our node that participates in recovery itself goes down? How are we going to handle this situation? So again, if we go back to our cluster of 4 nodes, we can imagine node 3 fails. So the whole cluster loses the connectivity to this node, and after some time, our leader decides to initiate the recovery. So based on recovery points, as we saw, it's going to detect which tasks should be recovered, and it will redistribute them among active nodes. So some work might go to node number 2, some work might go to node number 4. But in this scenario, node number 4 goes down as well. So it didn't have enough time, probably, to update the recovery points and say that this work now belongs to node number 4. And still belongs to node number 3, but it was not processed. So we have orphan records, and we cannot say that the node number 3 has been successfully recovered. So how we can handle this situation? In order to do that, we can extend our supervision protocol, and we can introduce 2 more things. We're going to introduce the recovery acknowledgement message, which is going to be sent from the node that does the recovery back to the leader who initiated the recovery, saying that it has handled all the requested work to be done and is successfully accomplished. And moreover, this communication is going to be controlled by a recovery timer. So we will decide how much time we need to recover a single node. And if we didn't get acknowledgement from all nodes participating in recovery until the time we set, we can not say that the node has been successfully recovered. So let's see how it's going to change this scenario. So node number 3 goes down, and now the leader, when it starts the recovery process, the first thing it does, it sets up the recovery timer. So this timer, again, is going to put time boundaries for all nodes to handle their portion of work and send back to the leader the success message saying that it has successfully restored everything. So now, when we send some work to node number 2, and once it's done, node number 2 is going to reply us back saying, I handled my work, everything is fine. Meanwhile, node number 4 receives its portion of work, but it fails. So leader didn't receive a successful message from node number 4. Eventually, our recovery timer will fire an event that we didn't get all acknowledgements from node number 2 and node number 4. And there's something weird going on. So the leader will reinitiate the recovery process for the failed node number 3. It's going to reset the timer, get again, based on recovery points, which tasks have not been restored, do its work, get the acknowledgement from all nodes, and only then it will cancel the recovery timer. And it will consider that node number 3 has been successfully restored. Let's see a trickier scenario. What happens if the leader itself goes down? How are we going to handle this situation? So node number 3 fails. As we decided, we're going to start first the recovery timer, and we're going to initiate the recovery after that. But in this case, our leader went down, and we lost our recovery timer, and there is no longer anyone responsible for orchestrating the recovery process. How are we going to deal with that? The answer is quite simple. What we can do, we can start the recovery timers on all nodes in the cluster, but still only the current leader of the cluster is going to orchestrate it. So let's see how it will change the scenario. Now, for the failed node number 3, we have the recovery timer started on all active nodes of the cluster, node number 4, 2, and 1, which is our current leader. So the leader proceeds to detect, based on recovery points, which work should be handled. It goes down. With Akka clustering, eventually, we will elect a new leader. For example, this might be a node number 4. And sometime later, our recovery timers responsible for the failed node number 3 will trigger an event that there was no acknowledgement that it was recovered. Node number 2, based on this event, will not do anything because it's not the current leader. It will just reset the timer. Node number 4 will see that it became the current leader of the cluster. Now it's its responsibility to reinitiate the recovery process of failed node number 3. So it will be node number 4 who will go, based on recovery points, detect which work should be restored, redistribute between active nodes in the cluster, get the notifications that it was successfully handled, and then it's going to cancel the recovery timer on both of the nodes. Node number 4 and 2 will get this message that node number 3 has been successfully restored. This is a message that will be broadcasted among nodes of the cluster. So now I would like to do a demo for this scenario. Again, we will have a cluster of 4 nodes with different states, and we're going to shut down our node number 3, and we'll see how the cluster will react on it, and we're going to unexpectedly shut down the leader as well. And we'll see how a new leader is going to be elected, and we will still finalize our recovery process. So it's exactly the same layout. From top left, we have node number 1, 2, 3, and 4 in a clockwise direction. They also have states, so we can see on a dashboard what's going on. So as I said, we're going to shut down the node number 3, and we're going to shut down node number 1 as well and see how the new leader will be elected. So in the metrics, we can see that for simplicity, node 1 does not have any records because we're going to kill it too. Node number 2 has 2 records, node number 3 has 3, and 4 has 4 records. So now we'll go ahead and kill the node number 3. So we see that the process has been completed for the node number 3. We can shut it down. And we'll see again the whole cluster trying to connect to the failed node for a while, printing lots of logs. And we'll see that eventually our leader will decide that the member is not up, and it will try to reinitiate the process. But we throw an exception to make to simulate that it went down as well. So in the logs, we can see that it detected that node number 3 is unreachable. Then it decides to remove it after some period of time to make sure that it is not a network latency. And then I'm printing a message saying that it's going to die, but it's part of simulation. So it got some runtime exception, which gives me an ability to shut down the node and simulate unexpected shutdown while it was trying to recover the failed node number 3. So we can see the process has been completed. We can close it. So after some time, the leftover left nodes, node number 2 and node number 4, will get an event that a leader has changed. So we can see it in the logs. In this example, the new leader is node number 2. And node number 4 is also aware that the leader has changed, and it's node number 2. So here is the message. Again, some time goes by, and eventually our recovery timers that were responsible for node number 3 are going to fire an event that there was no acknowledgement of successful recovery of the failed node number 3. So we can see this message in one of the nodes, which is our leader. Resurrection has timeout for the originally failed down host. And now it sees that it's the current leader of the cluster, and it's its responsibility to finalize the resurrection of node number 3. So in the logs, we can see that it's registering the down host and it's starting the resurrection. So again, based on recovery points, it has detected there were 3 in-flight records that used to belong to node number 3. And now it's going to redistribute them among active nodes of the cluster, which is just node number 2 and node number 4. So you can see the requested resurrection from one host for 2 records and another request for 1 record. So we can see that the leader itself received 2 records for resurrection for the down host. It has successfully processed them. And we can see similar messages on our node number 4, which we asked just resurrect 1 record. So we can see that it's acknowledging the resurrection and successfully accomplished it. We can see 2 confirmation messages from node number 2 and node number 4 that it did a job for 2 records that we have requested. And 1 confirmation message from node number 4 that it has resurrected 1 record that we have requested. So these were all records that we had on node number 3, and based on that information, we can decide now that there was a successful recovery of the failed node number 3. And this message is broadcasted between 2 nodes, and they can cancel their timer. So we can also see this in a dashboard. So we can see that the states of our nodes has jumped from 2 records to 4 because node number 2 picked up 2 records from the failed node number 3, and node number 4 got 1 record. So it had 4 before, now it became 5. We can also see the event that has happened, that the host went down and it has been handled by a new leader. So I'm going to zoom in on this event. So we can see that node number 2, which is our current leader, has actually recovered 2 hosts, which is node number 3, or the originally failed one, and the leader, the node number 1. It just didn't have any records. And we can see also the events reported that how many records have been accepted by different nodes after the resurrection. So node number 2 accepted 2 records, and node number 4 got only 1. So this helps us to see the progress, the state of our nodes, and control the progress of recovery and make sure that it's working. So Akka cluster supervision gives us a tool to create an event-driven supervision framework for our services and be able to react on any failures and restore the in-memory state we don't want to lose, or recover interrupted processes we want to run till the end. There are also different ways you can extend the supervision protocol. For example, you can introduce multi-data center support, which was introduced in Akka clustering not so long ago, and you can integrate it into your supervision protocol, and you have multiple clusters running with different leaders, but still be able to supervise each other and detect that the whole data center went down. You can also introduce smart task distribution. In my example, we just did simple even distribution between active nodes on the cluster, but you can also take into consideration current node loads or number of nodes participating in recovery, or overall data center health. For example, if the whole data center is not feeling well, you can switch the recovery to a new data center. You can also create adaptive recovery timers. In our example, it was just a configurable setting, but you can make it smarter and adapt to the network latency, or the number node of the cluster, or what was the original load of the node that just went down. So this is just a prototype we're testing right now, and it's look really promising. And maybe eventually we'll go to production in our services. So if you have any questions, you're welcome to ask.
Hi. If I look at your strategy, it looks like that all your data is not tightly coupled. We do have tightly coupled data, which is distributed around the cluster. And the problem we have is that as soon as the node dies, all your actor waves become invalid. Do you deal with that? And if yes, how do you do that?
So you say that, I didn't get, so you say that the data is tightly coupled?
Yeah, if you have two nodes, A and B,
yeah.
and there's an actor on A that talks to an actor on B, and as soon as B dies, then all your actor waves that point to that actor on B become invalid, because it's tightly coupled to that actor's life cycle. And if you then resurrect that actor on a different node, then you still need to find it back somehow.
So it's based, when I showed the persistence you're doing for recovery points, you can restore any metadata you want. And if you want to have a parent-child relationship between your actors, it's up to you to define what's the recovery process of your actor. This framework just notifies you that there's something going on, and based on your own recovery points, you're able to handle them and do the recovery as you wish. You can recreate the whole tree structure of your actors, which are tightly coupled to each other, or you just create a single actor representing a state.
Yeah, okay, but then you fully reliant on databases then?
Yes.
Okay.
It's different from, for example, Akka persistence, where you need to persist the whole log of the messages. Here you really pick and choose what you want to supervise and what you want to recover in case of the failure.
Okay, yeah.
I worked in a project in the past where they were trying to use Akka cluster exactly for communication between nodes. And something that ended up happening is we ended up having lots of problems with the cluster state. So in the beginning, we didn't know, but there was an auto-downing mechanism, maybe rings a bell. We trusted that thing, didn't work. Sometimes our cluster was downing a member, and while that was happening, we couldn't send any messages. We didn't understand what was happening. Then we decided to implement our own downer. After we did that, we had some other problems. My bottom line is, did you guys have problems with cluster state consistency that would make it so that the messaging wasn't working as expected? I would assume yes, because I saw this Datadog diagrams, which probably is what you guys use to debug, but that's exactly the question. What are the strategies for debugging that you guys use to learn how to fix it, and did you guys have a lot of problems with that or not?
Thanks. So as far as I remember, auto-downing is not recommended when you start using any supervision or singletons in your cluster, because it can lead in a weird states. And it's pretty tricky to debug sometimes, and sometimes there can be network issues and maybe a fault event that the node actually went down, but it was just a blip in the network. So you just need to configure your service to be more sensitive to the current environment. And there are different tricks how you can decide if the node is really down or it's just a network. It's a hard, yeah, we also have problems. Right now we're just testing it.
Hi, thanks a lot for your talk. I have a question. What is going to happen when leader send a message to, let's say, actor A to resurrect actor 1 to resurrect actor 3, get acknowledged, but leader fails to perceive the state change that actor 2 picked up actor 3 resurrection. So it got acknowledged, but at this moment it failed, and database was not changed. How you handle that?
So if the leader failed to get the acknowledgement message?
So acknowledgement came in,
yeah,
but now leader has to update that node 2 picked up node 3 for this specific message, right?
The update of recovery points is happening on the node that does the recovery. It's not the leader that does that. And the acknowledgement message is sent when you recovered your state and you updated the recovery points to say that now it's on a new node.
Oh, okay, so it's not the leader. Okay, thank you.
One question, how does maintaining all these recovery points affect performance? Like whether there is any reason still to go stateful in this case, or it's maybe easier to switch to stateless processors?
Yeah, thank you. In our cases, because, for example, we're presenting orders, our original services, they're just standard CRUD operations, which sometimes leads to lots of unnecessary reads and writes to our databases. And sometimes when you want to supervise, the standard practice is to poll for work and make sure that it has accomplished, which creates lots of read requests. In this example, you just create one write and you do read only in case if something going bad. So when we did the math and we ran the test, it was much more efficient to just persist the recovery points and use them only in case of the node failure. So it gives us only 2 writes when we originally create the record and when we marked it as done. And we did multiple reads in case of the whole node failure. It depends, I think, on your business flows. In our operations, it was much faster to keep the state in memory and do updates in memory rather than updating the database and create just one recovery point that is going to supervise them.